All right, welcome everyone. So today, first of all, it's exam day for some people. So this week in recitation, we have our first exam in the course. So it'll be covering learning outcomes L1, L2, L3, and L4. So make sure you read through the exam setup guide on our course website. And then shortly before your scheduled recitation section, you'll get the Zoom meeting link for the proctoring session. So just keep an eye out for that. All right, so today for lecture, what we're going to be doing is we're going to be finishing up limits at infinity. And then we're going to be talking about tangent lines and instantaneous velocity. And those are really going to introduce our next major topic in the course. All right, so let's first though continue on with limits at infinity. And where did we leave off? We left off with this limit here. So the limit of x cubed plus x squared over 4 minus x squared as x approaches infinity. We're going to look at this example. And this is another one of our indeterminate forms where, as we're going to see, the numerator is getting large, the denominator is getting large, and we're not sure what's happening. Does the top win? Does the bottom win? Or do they sort of balance each other out? All right, so let's see exactly what's going on here. So if we look at this numerator, it's x cubed plus x squared. And those two terms are getting large positive. Now if we look at the denominator is 4 minus x squared. And if we look at those terms, what's happening? Well, those are getting ultimately large negative. And so we have this large positive number being divided by a large negative number, and we want to see what happens ultimately to the overall fraction. So this is another one of our indeterminate forms. And so our strategy for fractions like this is to use our x to the power n method. And that's what we're going to do. So we're going to look at this limit as x goes to infinity of x cubed plus x squared all over 4 minus x squared. And what did that method say? Well, it said let's look for the largest power of x in the denominator. So first of all, what's our largest power of x in the denominator? It's x squared. And we're going to multiply by a fancy 1. So we're going to multiply the numerator of our fraction by 1 over x squared. And we multiply the denominator by that same thing, 1 over x squared. So this is a common strategy that we use for these types of indeterminate rational functions, where we identify the largest power of x in the denominator and then multiply both the top and the bottom by 1 over that largest power. All right, so if we do our arithmetic there, let's distribute the 1 over x squared to the x squared term and to the x cubed term. And when we do that, we get x plus 1. And when we do the same thing for the bottom terms, we're going to distribute to the 4 and to the minus x squared. What do we get down there? Well, we get 4 over x squared minus 1. And we're doing the limit as x goes to infinity. And so at this point, we want to investigate what's happening to the top, what's happening to the bottom. So we're going to separate these and just consider, well, what's happening to that x plus 1? So as x gets really large positive, if we add 1 to it, we're going to have a large positive number. So this limit is infinite. And then same thing for the denominator. Denominator, we're going to investigate that limit as x goes to infinity. So limit of 4 over x squared minus 1. And we know that 4 over x squared term, kind of our whole reasoning for this method, is those fractions with x in the denominator go to 0. So this limit is -1. And so what we ultimately have here, if we put these together, is our numerator is becoming large positive, and our denominator is getting close to -1. So if we take a large positive number and divide by a negative, well, what's happening is we end up with a large negative. So we end up with a large negative number. And so the limit here is -infinity. So with these indeterminate forms like infinity over infinity, this x to the power n method is a common strategy. And the reasoning behind it is because we need 0 when we're to do the arithmetic. And so why this works out is precisely what we saw here, is that this limit of 4 over x squared goes to 0. And so we can do some arithmetic with 0. We can't do usual arithmetic with infinity. All right, so let's try another example. There's a whole bunch of indeterminate forms that we're going to be seeing. So far we've looked at 2 fractions. Next, let's check what happens if we have subtraction. And that's what we're going to look at in this example. So the limit of x cubed minus x squared as x goes to infinity. Now this is a different type of indeterminate form. And let's see what's happening here. So if we look at that x cubed, what's happening with that x cubed? X is going to infinity, and so x cubed is going to infinity. And maybe I'll put the arrow a little bit differently there. So x cubed is getting large positive. And then what's happening with the x squared? Well, that's also getting large positive. And then we're subtracting. So we have this large positive number minus another large positive number. And so there's a question here. Does that first number win out? Does the second number win? Or do they sort of balance each other out and kind of approach some number in the middle? And our strategy for this type of indeterminate form is to usually try to rewrite it as a product. And that's what we're going to do here. So x cubed minus x squared as x goes to infinity, we're going to factor this. So if we factor our function, we can factor it as x squared times x minus 1. And now we can look at each of those factors. We can look at the x squared, and we can look at the x minus 1. So what is the limit of x squared as x goes to infinity? Well, x is getting larger and larger positive. X squared is also going to get larger and larger positive. Same thing for x minus 1. As x approaches infinity, so as x gets larger and larger positive, x minus 1 is also going to get larger and larger positive. So both of those factors are getting really large positive. And so if we put those together, essentially what we have is a large positive number times another large positive number. And we can deal with multiplication. So if we have a large positive number times another large positive number, the result is a large positive number. So we say that this limit then is positive infinity. So these differences where we have a large number subtracted from another large number, it's not clear which of those numbers wins. Does the first number win? Does the second number win? Or do they kind of balance each other out? But when we're talking about products, it's a little bit clearer with multiplication. So if we have a large number times another large number, the result is going to be a large number. All right, let's try another one of these difference ones with subtraction. All right, so we have the limit as x approaches minus infinity, so something a little bit different, going in the other direction. So remember, x approaching minus infinity is where we're moving way to the left. We're looking at the left end behavior of this function. And our function here is square root x squared plus 25 plus x. And we're going to look at each of these individual pieces. So we're going to look at first the square root term. What is this term doing as x gets large negative? Well, when we take a large negative number and we plug it into just that square root piece, the squared there, the x squared, is going to make the negative positive. And then when we add 25, it'll still be a positive. And then when we do the square root, it'll still be positive. So this first term, square root x squared plus 25, is actually going to be getting larger and larger positive. So it's going to be approaching infinity. Now what about that second term? Well, x is approaching minus infinity. So when we add x to it, we're actually adding in a large negative number. So it's almost like subtraction. We have a large positive minus a large minus another large number. So this is another indeterminate subtraction problem, infinity minus infinity form. And so we don't know, does that square root term win? Does that plus x at the end win? Or do they sort of balance each other out? And this one probably isn't so clear, because with the square root x squared, how is that behaving? Square root functions are notoriously difficult to work with. So we're going to see how to handle it in this example. And what we're going to do is one of our usual kind of tricks with root functions, and that's to use the multiply by the conjugate. So let's start with our limit that we want to do. Limit of x squared plus 25 plus x as x goes to minus infinity. So we're going the other direction. And what we're going to do is we're going to kind of use our standard conjugate trick of multiplying by a fancy 1. And to help us out, I'm going to rewrite our original function as a fraction by just putting it all over 1. So I'll have square root x squared plus 25 plus x all over 1. And then we're going to multiply that by our conjugate term. And so how do we do the conjugate of that term in the numerator? Well, we just basically rewrite it. So square root x squared plus 25 and then x. And then the only difference is we switch the plus to a minus. So it'll be minus x. And then we do the same thing for the denominator. So that's our standard kind of conjugate trick of multiplying by a fancy 1. Now let's actually go through the multiplication there in the numerator. And we know from kind of doing this type of thing before, we get a lot of canceling. So doing the limit as x goes to minus infinity. And so let's multiply the terms out. So when we multiply those square root terms together, basically the square roots cancel and we're left with x squared plus 25. Then let's multiply the plus x with the minus x, and that gives us minus x squared. And then we can do it, it's good practice, but we know that when we multiply the plus x with the square root term, and when we multiply the negative x with that square root term, those will end up canceling. So really, this is all we're going to get when we multiply out those terms in the numerator. And this will all be all over. I'm not going to write the 1. It'll be over x squared plus 25 minus x. And so if we go through our arithmetic there in the numerator, can do a little bit more canceling. So we see the x squared and the minus x squared, so those cancel. And what we're left with then is 25 over square root x squared plus 25 minus x. And we're doing the limit of this as x goes to minus infinity. So at first glance, it seems like we've made it more complicated. We've taken a non-fraction and we've made it into a fraction. So it seems like we've made it more difficult. But if we investigate the behavior of what we have here, let's look at just that term in the denominator. So if we look at just that term in the denominator, limit of square root x squared plus 25 minus x as x goes to minus infinity, what do we have here? Well, the first term we said was going to positive infinity, just becoming larger positive. And now we have a negative x. X is becoming large negative. Negative x would become large positive. So it's almost like a double negative here. And so the result is a large positive number plus a large positive number. And that we do know something about. So the issue only comes if you have subtraction. So because we have a large term that's going to positive infinity, and then a second term that we're adding in that's also going to positive infinity, the result goes to positive infinity as well. And so that's what's happening in our denominator. Putting that all together then, what we have here is we have the limit of this fraction, but the numerator is 25, and we're dividing by essentially a large negative number. So, or a large positive number rather. So we have this fraction where the numerator is staying 25, but our denominator is getting larger and larger. So whenever we have a fraction that's behaving like that, where our numerator just approaches some number and our denominator gets large, either positive or negative, the result then is it goes to 0. So the limit of this fraction as x goes to minus infinity is equal to 0. And so this example is showing us that when we have an indeterminate form like infinity minus infinity, it is definitely a possibility where those two terms that are being subtracted sort of balance each other out. And in this case, they balance each other out very nicely. They balance down to 0. So the limit of this function square root x squared plus 25 plus x, as x goes to minus infinity, is equal to 0. They kind of balanced each other out. So that's just another technique. And usually when you see a square root function plus something else, you start thinking along the lines of this conjugate strategy for multiplying by the conjugate term. Okay. So we're going to break for a little bit from indeterminate forms. And in the next example, we're going to look at how to kind of convert regular limits. So the sort of thing we were doing earlier, last week and the week before, how we can convert those limits, where like x approaches a number, into limits at infinity. And sometimes this is helpful. We don't always have to do this, but sometimes it's helpful to do this. And usually where it becomes helpful is with composite functions. So if we look at this limit, the limit as x approaches 0 from the left of e raised to the 1 over x, let me get a different color. That 1 over x term is really an inner function. It's behaving, it's really, we have a composite here. The exponentials are our outer function, and then that 1 over x is our inner function. It's inside the e raised to the whatever. So it's inside the exponential function. And so our strategy here is going to be what we generally call like a change of variables. And so the first step for this is just to call that inner function, just give it a name. So we're going to call it u. So we're going to let u equal 1 over x. So that's step 1. Step 2 is we're going to compute the limit of u, and we're going to compute the limit as x approaches 0 from the left. So whatever x is approaching in our original limit, that's what we're going to calculate right here. We fill in our value for u, and we calculate this. And what do we get? Well, we get minus infinity. So the limit of 1 over x as x approaches 0 from the left is minus infinity. Why is it minus infinity? Well, you can kind of go through the full explanation, but just to give you a little bit, this is one of our c over 0 forms. So that means it's an infinite limit. And then you can use a test number then to figure out, is it positive or negative. So your test number might be maybe like negative 0.1. So something close to 0, but a little bit to the left. So when you plug negative 0.1 into the function 1 over x, you get a negative result. So the limit here is minus infinity. So if we were to write this out just a little bit differently, what this is really saying is that as x approaches 0 from the left, our expression for u is approaching minus infinity. And that's going to allow us to change the variable in our expression and then to change the limit that we're really considering. So that's the final step, is originally we were interested in the limit of e to the 1 over x as x approaches 0 from the left. But what we're going to do instead is we're going to change all of those x terms that we have, and we're going to change them to u's. So we look in our expression up here, and we see an x term here. And we know what 1 over x is. We said that was u. So we'll change that to e to the u. And then we also have this x approaching 0 from the left in our expression. And in step 2, we figured out, well, what does that mean for u? And what it meant is that u was approaching minus infinity. So we took the 1 over x, we changed it to u. We took the x approaching 0 from the left, and we changed that into u approaching minus infinity. And now this is one of our kind of basic infinite limits that we looked at last time, for the e to the u function, for our general exponential function, when you move very far to the left, this limit is 0. So you get closer and closer to the x-axis. And so that means the original limit we were interested in is equal to 0. So this is sometimes a helpful strategy when we have these composite functions and we see that the inner function is either going to plus or minus infinity. All right. Let's try another one of those. Okay, so inverse tan of 1 over x minus 2, and we're doing the limit of this as x approaches 2 from the right. If we look at this, we see that same sort of behavior where we have an inner function and if we think about what's happening to that inner function, as x approaches 2 from the right, we get, as we're going to see, it's going to be positive. The limit of that is going to be positive infinity. So as we plug numbers that are closer and closer to 2 from the right, that expression inside the arctan function is getting really large positive. So we're going to go through the same process. Step 1, we're going to change our variable to u. So we're going to let u equal that inner function, 1 over x minus 2. And in step 2, we're going to compute the limit of that value for u. So we're going to do the limit of u, and we're doing it as x approaches 2 from the right. So we'll keep that the same. Let's fill in what we said u was. So it'll be 1 over x minus 2 as x approaches 2 from the right. And if we look at that, it's another one of our c over 0 forms. So, if we were to plug 2 directly into that function, we would get 1 over 0. So it's one of our c over 0 forms, which we saw for infinite limits meant either positive infinity or minus infinity. And we have to decide which. Is it positive or negative? And so we might use a test number that's close to 2, but a little bit bigger, so maybe like 2.1. So close to 2, but we add a little bit on. And when we plug that in, we would get 1 over a positive number. And so the result here we would see is positive infinity. So this is one of our infinite limits. So what that actually means then, if we kind of rewrite this, is that as x approaches 2 from the right, our new expression u is approaching positive infinity. It's getting larger and larger positive. So we're going to use that then in step 3 to just fully rewrite our limit. So we have our inverse tan function of 1 over x minus 2. And we're doing the limit as x approaches 2 from the right. And the idea is we want to rewrite the 1 over x minus 2, and we want to rewrite this x approaching 2 from the right. So we want to change all of our x terms into u. So let's see how that looks. So our inverse tan will still be there. And then we said 1 over x minus 2 was u. And then we said Well, as x approaches 2 from the right, what's happening to u? Well, u was approaching positive infinity. So we're going to change our limit then so that it's the limit as u goes to positive infinity. So we've produced this new limit to consider, the limit of arctan of u as u goes to infinity. And this is also one of our basic forms that we saw last time. This is one we just kind of have to remember. The limit at infinity of arctan, where we go towards positive infinity, is pi over 2. And so the limit of our original limit is pi over 2. So we generally use this technique where we have an inner function and an outer function, and the inner function is going to either positive infinity or minus infinity. And that's what we saw in both of these. We had 1 over x in the first example for our inner function, and then 1 over x minus 2. And in each case, that inner function was going to either plus or minus infinity. And so we kind of rewrote it using this change of variables so that in the end, it ended up becoming just one of our basic forms that we really just have memorized. All right, let's try one more kind of example just to summarize everything that we've done in this section for this learning outcome. And this is going to be one of our trickier limits at infinity. And spoiler, it involves the square root sign. So square roots always add an element of trickiness. So in this example, we're going to find all horizontal asymptotes of the function square root of 4x squared plus 1 over 3x minus 5. So we want to find all horizontal asymptotes. So at most, we could have 2. Might only have 1 horizontal asymptote, or we might have none. And so to find all of them, that means we need to do 2 things. We have to calculate the limit of our function as x goes to positive infinity. And then we'll also have to do the limit of our function as x goes to minus infinity. So let's do positive infinity first. So we're going to do the limit of square root 4x squared plus 1 over 3x minus 5 as x goes to infinity. And we have this fraction, so we're going to use our standard trick of multiplying by 1 over the largest power in the denominator. So if we look at this, what is our largest power of x in the denominator? It's just x. So we're going to multiply everything in the denominator by 1 over x, and then we'll do the exact same thing in the numerator. Now, we need to be careful here because we're multiplying in the top here, we're multiplying a square root by something that doesn't have a square root. And so to help us along, what we want to do is we want our square root term here and our 1 over x, we want these to match. So we want them to look similar. And so to do that, we're going to introduce a square root in that 1 over x term. So since x is approaching infinity, it is ultimately positive. And so what that means, and I have a few helpful properties over here that we're going to be considering. is we're going to rewrite that 1 over x term using the definition of square root u squared. And so when x is approaching infinity, it means it's positive. So if we look at the definition of square root u squared, when u is positive, when the number underneath the square root sign is positive, the square root u squared is equal to u. So that means for us, x is equal to the square root of x squared. And so we're going to rewrite this limit then as square root 4x squared plus 1 times 1 over square root x squared. So the square root and the squared, you could think of it as they sort of cancel out here when x is positive. Now in the denominator, we don't have the issue with the square root, so we're going to leave the 1 over x alone in the denominator. And what we'll do there is we'll just take the 1 over x and we'll do our usual kind of distribution. We'll distribute it to the 3x and to the minus 5 there. So when we do that, we get 3 minus 5 over x. All right, so we did our usual 1 over x to the power n trick. We had a square root, and it was just a square root term by itself. It wasn't square root plus anything, so we couldn't really do a conjugate method. And then we introduced a new square root for that 1 over x by just observing that because x is positive, x is equal to the square root of x squared. And why do we want to do that? Well, when both terms have a square root on them, this other property up here says we can kind of bring them all under one common square root sign. So say if we had square root of a divided by square root of b, we could rewrite that fraction instead as just the square root of everything, square root of a over b. And that's what we're going to do, is we're going to bring those terms underneath the same square root sign. So we're doing the limit as x goes to infinity, and we're going to rewrite that everything in the numerator with just one big square root. So it'll be square root of 4x squared plus 1 times 1 over x squared, and then we'll leave our denominator alone for now. And then if we distribute there, the 1 over x squared, kind of go through our usual distribution, we'll distribute it all under the square root sign now. And when we do that, we'll get 4 plus 1 over x squared. All right, so we have the limit as x goes to infinity of square root 4 plus 1 over x squared divided by 3 minus 5 over x. Now we can use our limit laws, which essentially allow us to split up our limit and bring it underneath the square root sign. So we can write this as the limit, or the square root of the limit of 4 plus 1 over x squared as x goes to infinity, divided by the limit of 3 minus 5 over x as x goes to infinity. And we know each of those 1 over x and 1 over x squared terms go to 0. So this ends up being square root of 4 plus 0 divided by 3 minus 0, which ends up simplifying to just 2 over 3. And so what this shows us is we did the limit of our function as x moves to the right, as x approaches infinity, and we got this value of 2 over 3. So this means we have a horizontal asymptote at y equals 2 over 3. So that's one possible horizontal asymptote. Now, that's for the right direction. We want to look at what happens as we move to the left. And something completely different could happen on the left side. So we need to consider that separately. We'll be able to reuse a lot of this same work, but where the issue is going to happen is, and we're going to see we get a different result, and where that's going to happen is right when we did this observation. So here we said that because x is positive, x is equal to square root x squared. When we do the other limit, x is going to be negative, and that doesn't quite work out that way. So let's try that next. So we're going to do the limit as we go to minus infinity now of our function. And that's because we want to find all horizontal asymptotes. So the left side of our curve could be doing something completely different. So let's fill in what our function is. We're going to do the same trick of multiplying both sides, both the top and the bottom, by 1 over x. And now our observation, we want this 1 over x term to match up with our square root. So we want to introduce a square root term there. So we really want those terms to match. But because x is approaching minus infinity, it's negative, or it's ultimately negative. And so what does it mean for the definition of this square root of x of square root of u squared function when we're trying to plug in a negative number? Well, it's defined a little bit differently. So square root of x squared then would be equal to negative x for x negative. So we want to replace this x by a square root term. Well, in order to do that, we need to plug in instead negative square root x squared. And, you know, if you're not convinced with this, try it out with a number. So maybe like something like x equals negative 3. So if I were to plug negative 3 into the negative square root of x squared, what would I get? I would get negative square root, negative 3 squared under the square root, which becomes just positive 9. And then the square root of positive 9 is 3, but we have a negative in front of that, so it becomes negative 3. And so this is just equal to x in our little example here. So it really does check out. So this might seem like a weird definition, but it turns out it's also the definition, or one of them, one way to define the absolute value function. All right, so if x is negative, we want to change that 1 over x to a square root term in the numerator, but now we have to throw in an extra negative in order to do that. So we're going to have 4x squared plus 1 times, and it'll be 1 over the square root of x squared. And then for our denominator term, that's the same as what we saw before. So 3 minus 5 over x. All right, so why did we want to introduce that square root? Well, we have this property that says when we're multiplying or dividing two square root terms, we can just bring them all underneath the same square root, just one big square root sign. And that's what we're going to do here. We're going to combine those terms in the numerator into just one big square root. So we'll have the square root of 4x squared plus 1 times 1 over x squared. And then this will be all over 3 minus 5x as x goes to minus infinity. And what happens to that negative? Well, that's a constant multiple, so we can just put that in front of this big square root. So it'll be negative 1 times the square root of 4x squared plus 1 times 1 over x squared. All right, so we go through the same arithmetic now that we had before. We just have this extra negative. So we simplify just like we did. We end up with 4 plus 1 over x squared over 3 minus 5x as x approaches minus infinity. We can bring the limit, we can split the limit up and bring it underneath the square root sign. And x is approaching minus infinity. And do the same thing for the denominator. X is approaching minus infinity. And then if we do the arithmetic there, or calculate those limits, the 1 over x's all go to 0. And so we end up with negative the square root of 4 plus 0 divided by 3 minus 0, which ends up being negative 2 over 3. So we get a different number on the left for the left end behavior. And so we conclude that we also have, let's say, we have two of them now. We also have a horizontal asymptote at y equals negative 2 over 3. So the left end behavior is doing something different than the right end behavior. So normally with square roots, you always want to be careful because they tend to cause problems, as we kind of saw in this. So this is really about as difficult as it gets here. It's a little bit more of a nuanced argument for dealing with, those negatives and positives there in our definition of absolute value. All right, so that's what we're going to cover for limits at infinity and how they can be used to calculate horizontal asymptotes of a function. Our next topic is going to introduce kind of the major theme in the course, and that's derivatives. So what we're going to talk about next is the slope of a secant line to a curve, and how we can use limits then to find the slope of the tangent line, and then also how we can find the average velocity of a moving particle, and then use limits to find the instantaneous velocity of that particle or some moving object. So it's going to be two kind of applications here, and the calculations are going to be very similar. And we're going to start with tangent lines. So we're going to start with the case of the tangent line at a point P on the circle. So in our little diagram here, we have a circle, and we have our tangent line at point P. And what do we notice? So what are some of the characteristics of a tangent line? Well, if we look at where the tangent line kind of touches the circle, it really just touches it. It doesn't intersect it twice or anything like that. So our tangent line should just touch the circle at point P. And what else do we notice? You know, if we think about tangent lines, what do we want in a tangent line? Well, if we were to get very close to P, and that's kind of what we're seeing in that second picture there. So if we get very close to point P, if you notice, really close to point P, it's hard to tell the difference between the tangent line and the actual circle. So our tangent line gives a very good approximation of what the circle is doing at point P. And we can see that, like I said, in that second picture, where right at point P, right around there, the tangent line and the circle, it's hard to tell the two apart. So another way to kind of think of that is that at point P, the circle and the tangent line they really have the same slope. They're going in the same direction. So imagine moving along that circle. If you were moving along that circle at point P, you would be traveling in the exact same direction as that tangent line. And so it's that idea of sort of slope and direction that's going to be the main focus of how we actually develop this tangent line for just general curves. And so the question is, well, how do we construct a tangent line for just a general curve? Well, when we think of lines, we normally think that there's 2 points that define a line. And so how we're going to do this is we're going to use secant lines. So we're going to use a secant line. So a line that intersects our curve twice. And then we're going to let that second point move closer and closer to the point that we're interested in, point P. So we're gonna kind of sneak up on how we define the tangent line. We're gonna say, we're interested in point P. Let's find a second point on our curve, point Q. And since we have 2 points, we can connect a line between them. And that's called a secant line. And what we're going to do is we're going to move that point Q so that it gets closer and closer to point P. And that's going to give us our tangent line. So in this diagram here, we have our curve, y equals f of x. And then the line connecting points P and Q, that's our secant line. So that's our secant line. Both P and Q are on the curve, and then we have a line connecting those 2 points. And then the line down here, this is sort of what we're after. This is what we want. We want our tangent line at point P. And so like we said, how we're going to do that is first we construct the tangent line, and then we're going to move point Q so that it gets closer and closer to point P. So let's see how that would look. And hopefully this looks all right. We're going to do a little animation here. So we have this graph of our curve and points P and Q, and then the secant line. And we're going to watch to see what happens in this animation. We're going to watch to see what happens as point Q moves closer and closer to point P. So let's turn the animation on. And right now Q's moving away. But once Q starts moving closer and closer, we see that the secant line becomes pretty good. It gets closer and closer to what we want for our tangent line. And same thing in the other direction. The other direction, as point Q moves closer and closer to point P, the secant line becomes closer and closer to what we want as our tangent. And then back, coming from the right, and then back as Q moves from the left. In either direction, as point Q gets closer and closer to point P, our secant line becomes more and more like what we want our tangent line to be. And so when Q is really close to point P, you can't even tell the difference between the tangent line and the secant line. So that's the idea, is we're going to be moving point P, or we're going to be moving point Q closer and closer to point P. And everything we've done in the course so far, we've been talking about limits. That's exactly what limits do, is they allow us to move something closer and closer to something else. And so we have all of the infrastructure now to talk about, to kind of take this idea and represent it mathematically. So that's what we're going to look at next. We're going to look at how we actually define this mathematically, and it's going to involve limits. So we're going to look at the slope of a secant line. Or the slope of a tangent line. And like we said, it comes from our secant line. So let's just unravel what this definition says. So M, this is usually what we're going to call our slope of the tangent line. Let me close out of the animation here. So M is going to be our slope of the tangent. And this limit as x approaches A, this is the idea of point Q moving closer and closer to point P. So that's how we deal with it mathematically, is we're doing the limit as we're doing some limit. We'll see why it's x approaches A in a second. And so the other piece of this, the f of x minus f of A all over x minus A, this is actually the slope of the secant line. So it's the slope of the line connecting points P and Q. Let's see where that comes from. So let's say we want to do the slope of secant PQ. How do we find the slope of a line? Well, it's the y-coordinate of one point minus the y-coordinate of the other point, divided by the x-coordinate of one point minus the x-coordinate of the other point. And so if we look at our graph, let's say point P is happening at x equals A, and point Q is happening at just some general x term. When we look at the actual coordinates of the point then for P, the way we find the y coordinate is we just plug in the a value into our function. So point P has coordinates a comma f of a, where a is the x value and f of a is the y value. And then Q has something similar. There the x value is just x, and then to find the y value, what do? Well, we just plug x into the function. So the y value is f of x. So when we find the slope of the line connecting those 2 points, we use our slope formula, and it's y coordinate of point Q minus y coordinate of point P. So f of x minus f of a. And then it's the x coordinate of point Q minus the x coordinate of point P. So x minus a. And we see that's exactly what we have. And so as x approaches a, or as point Q approaches point P, that's really the same thing as x approaches a. So we're able to define the slope of the tangent line as the limit as x approaches a of f of x minus f of a divided by x minus a. And it's really just the limit of our slope of our secant line as point Q gets closer and closer to point P. Now we do have an alternative form of this definition. And that's what we're going to look at down here. So there is another way to rewrite this. And it turns out this approach is going to be our kind of the main version that we use. So both of these are perfectly fine, but this version is sort of our main version. And so let's just see how the two of them are related. So sometimes instead of saying that Q happens at value x, we sometimes say, or we can alternatively say, that it happens close to a, but we add on a little bit extra. So generally when we're talking about limits, x is getting closer and closer to a. So we could say x it's just about a, but we're adding on just something a little bit extra. Something a little it's small, but just a little bit extra. And that's what this h represents. So h is usually small. Just some small number. So point Q is close to a, but we add on a little bit more. And so if we revise how point Q looks with that in mind, let's say it's now happening at a plus h. How do we find the y value? Well, we plug a plus h into our function. So we have the coordinates of Q in this sort of revised format are a plus h, that's our x coordinate, comma f of a plus h, that's our y coordinate. And so when we use the slope formula with these revised coordinates, what does it become? Well, it's the y coordinate of Q, which we're writing now as f of a plus h, minus the y coordinate of point P, which that stays the same, all divided by the x coordinate of point Q, so a plus h minus a. And then there the a's cancel. We have a minus a. And if we simplify that, we see that we get exactly what's in that second formula. So f of a plus h minus f of a all over h. And so that's just another way to think of the slope of the tangent line. And it might not look immediately like we're talking about the slope of a line in that formula, But it turns out that that formula is easier to do computations and calculations with. So ultimately that becomes another way to think of the slope of our tangent line is as the limit as h goes to 0 of f of a plus h minus f of a all over h. And again, that limit as h approaches 0, that's just really saying point Q is getting closer and closer to point P. All right. Let's try an example. So let's look at the parabola y equals x squared and point P with coordinates 1, 1. So let's actually find the slope of the secant line PQ, where Q is the point with coordinates 2, 4. And we're going to use our slope formula. And this one, everything's given to us. All the coordinates are given to us. So it just comes down to just plugging into the formula. So the slope of the secant line it's the y-coordinate of point Q minus the y-coordinate of point P. And the order doesn't really matter. You just have to be consistent. So if you put the Q coordinates first, you have to do it in the top and the bottom. So as long as you put the same point, the coordinates first in your subtractions there, you'll get the same results. So the order really doesn't matter. You just have to be consistent. All right, so let's plug in our coordinates. So the y-coordinate of point Q is 4. The y-coordinate of P is 1. So we get 4 minus 1 in the numerator. And then the x and the y and the x coordinates of point Q is 2. And then the x coordinate of point P is 1. So if we do the arithmetic, we get 3 over 1. So the slope of our secant line connecting those 2 points is 3. All right, let's try it again. But now we're going to look at a different point that happens to be a little bit closer to point P. So we're going to do the slope of the secant line PR for point R that happens at x equals 1.1. And so what we notice here immediately is that in the first part, we were actually given all the coordinates that we needed, both the x and the y coordinate. Down here, we're only given the x coordinate, so that means we actually have to calculate the y coordinate. So we have to calculate the y coordinate for point R. And how we do that is we take our x value, which in this case is 1.1, and we plug it into our function. So what is our function? Well, it's the parabola x squared. So we're going to plug 1.1 into the x squared function. And if we do that calculation, we get 1.21. So the y-coordinate of point R, if we wanted to write point R with both of its coordinates, it's 1.1, 1.21. So now we have all the coordinates that we need to do the slope, so we can just go through our slope calculation. So we'll do the y-coordinate of point R minus the y-coordinate of point P divided by the x-coordinate of point R minus the x-coordinate of point P. Just be consistent. So we put our y-coordinate first for point R, and we get 1.21 minus 1 in the numerator. And then in the denominator, the x-coordinate is 1.1, so we get 1.1 minus 1. And then if we do the arithmetic, we get 0.21 divided by 0.1, which ends up simplifying to just 2.1. So we see that the slope of the secant line connecting points P and R is 2.1. All right, so Next time we're going to actually do the calculations to find the slope of the tangent line, and we'll see how to do that next, or next time we'll finish this example. So we'll stop there for today. Just a reminder for everyone, this week, week 3, is our first exam during your scheduled recitation time. So, make sure you read through the exam setup page on our course website. Shortly before the exam starts, I will send out by email the Zoom meeting link. You can also find the Zoom meeting link for the proctoring session on our course calendar, but I'll also send it out by email. And like I said earlier, this exam for this week is going to cover learning outcomes L1 through L4. So everything we did up through and including continuity, continuous functions. All right, so we'll stop there. Good luck studying, and feel free to, if you have questions as you're studying, post on the discussion board on our GitHub page. And don't forget, we have office hours, so you can come to our office hours and ask questions as well. All right, have a good rest of your day, and we'll see you all for lecture on Thursday. Bye-bye.